Okay, welcome to the session of the Air and the Surface 1. And I am Meng Kai Li from Chinese Academy of Sciences. And we will have the first presentation, and the speaker is Jason Randal from Purdue University. And his topic is the next generation personal protective equipment for real-time inactivation of airborne biological threats, the part 1. Okay, welcome.
Okay, hello everyone. My name is Jason Randal, as you just said. I'm very excited to be here today, and I'm very excited to present my research on next generation PPE for real-time inactivation of airborne biological threats. As you mentioned, I'm the first in a 3-part presentation. So I will be discussing the experimental measurements that have been done in order to test for the efficacy of the devices that have been developed. I'm a graduate research assistant at Purdue University in West Lafayette, Indiana. So first of all, it's important to provide some background on the motivations behind this project. As we're all very aware right now, there is a present need for real-time inactivation of airborne biological threats. The COVID-19 pandemic made many more of us acutely aware of the need for this, but there are also a number of other viruses of concern, including RSV and M. tuberculosis. The existing technology that's usually used for this uses physical separation or filtration. The standard that's been set for that during the pandemic is N95 masks, which normally provide at least 95% separation of any particles that are at least a diameter of 0.3 microns. That does leave some area to be desired on top of that 95%. In addition to this, there is currently a lack of consistent testing methods for air disinfection systems. This presents a real challenge in determining the exact efficacy of devices that are presented or put on market, and it also presents the issue of comparison across devices. So from this, the goal of the project is to develop and demonstrate a mask-like PPE device that employs UVC lamps in order to inactivate airborne pathogens. There are constraints when using UVC for real-time inactivation. If you provide a sufficient dose of UVC to a wide range of viruses, such as SARS-CoV-2, influenza, and others, they have been shown to be effectively inactivated. However, the dose delivered to human skin and eyes must be kept below the threshold limit values. The threshold limit values are of a special concern when using PPE because the reactors are going to be so close to human skin and eyes. So keeping the values below this is a special consideration. 3 different reactors were tested using the methods that I'll be discussing today. The first, the Nichia reactor, uses Nichia brand LEDs, 4 of which were put around a PVC pipe. They each emit at a peak of 282 nanometers. The second reactor, the barber pole reactor, uses 27 LEDs on a strip. They each emit at a peak of 277 nanometers. They were wrapped in a spiral fashion around the PVC, similar to the Nichia. And the third reactor, the pod reactor, uses a low-pressure mercury lamp on the inside. All 3 reactors were fitted with a reflective material on the inside to increase photon recycling. The first step in the process was to measure the fluence rate field inside of the reactors. The fluence rate field depends on a number of variables, including the reactor geometry, the lamp power and placement, and any reflective material that's put on the inside of the reactor. The fluence rate field measurements that were completed experimentally were compared with results of numerical simulations that were completed. Those will be discussed in the second part of the presentation. The measurements of the fluence rate were conducted using the MFSD device. This was done because the MFSD probe accepts photons from approximately all incident angles, which is useful for measuring the local fluence rate inside of the reactors, especially when there's photon recycling happening or when there are multiple sources of UVC. If you have questions about this, Meng Kai Li will be presenting at the conference. In order to convert the values from the from the fluorescent measurements that are provided by the MFSD, calibration was done against an NIST calibrated radiometer. Used in combination with the MFSD was a positioning device. The positioning device allowed for precise positioning of reactors in order to take measurements using the MFSD at set locations. This allowed for movement in the X, Y, and Z directions. The reactors were moved rather than the MFSD to prevent any issues with the MFSD probe moving and values of the fluorescence changing from the probe. Measurements were taken at set locations inside of the reactors. For the LED reactors, these were taken at 10 different X cross-sections along the X-axis as shown in the left image, and then measurements were taken at 1 millimeter increments along the Z and Y axes. The measurements that I'll be presenting today are from inside of the Nietzsche reactor. The first measurements that were completed were when the reflective surface was included on the inside of the reactor. This plot shows each series is a different X cross-section, and then the measurements are shown at each Z location. And what's provided here is the fluence rate after it's been converted using the radiometer. These experimental measurements found a relatively consistent, relatively uniform fluence rate field. However, there were peaks shown along the walls of the reactor as well as at the center line. Along the walls is to be expected because that is where the LEDs were located for this reactor. Measurements were then taken with the reflective surface removed. The values shown are significantly lower than when the reflective material was included. So this demonstrated that photon recycling was critical to this reactor performance. To expand on the impact that the reflective material had on the fluence rate field of the device, this plot shows the amplification that was provided when comparing the measurements taken at the 8 centimeter cross-section. This cross-section was approximately where the LEDs were located. The reflective material provided an amplification that ranged between 12 times to 24 times, with an average amplification of 18 times. The center peak that was present when the measurements were taken with the reflective material was also not present when the reflective material was removed. The next step in the process was to complete biological experiments to test the level of inactivation achieved by the devices. The challenge agent selected for these experiments was T1 bacteriophage. T1 bacteriophage was aerosolized and then passed through the reactors once while the reactor was turned on and once when the reactor was off to determine the level of inactivation. T1 bacteriophage was selected because it provides a conservative estimate of UVC inactivation of a range of viruses of concern. As is shown here in the green, T1 bacteriophage requires a higher dose to achieve the same level of inactivation as of multiple different coronaviruses and influenza A. This was the setup that was used for the direct flow experiments to pass the challenge agent through the reactors. Nitrogen gas was passed through a one-port Collison nebulizer, which contained tryptic broth containing the T1 bacteriophage. This was then aerosolized and passed through the reactor, which was operated once on and once off. This was then sampled on the other end using a glass Impingor bioaerosol sampler. Here. And then from there it passed into a water trap, which was present to prevent moisture from going into the pump or the flow meter. The flow meter was used to ensure that the flow rate was consistent throughout the experiment, and the vacuum pump provided back pressure to maintain a constant flow rate. The flow rate that was used in these first direct flow experiments was 2.5 liters per minute. At this lower flow rate, the barber pole LED reactor was demonstrated to have an average inactivation of 1.83 log units. The Nietzsche LED reactor had a log inactivation of 2.4, and the low pressure mercury pod reactor, had an activation of 2.89 log units. Importantly, when compared against an N95 mask, which is in many ways considered the standard, that achieves 95% removal, or about nominally 1.3 log units. So all three reactors showed a higher inactivation than the removal of a N95 mask. The next experiments that were conducted were with the pod reactor at variable flow rates. This was done because the pod reactor provided physically meaningful measurements because of the use of T1 bacteriophage as a conservative estimate of inactivation, and provided geometrically relevant test setup because of the devices that were being developed are very similar in geometry to this reactor. The range of airflow rates that was used was 5 to 50 liters per minute to try to provide a representative flow rate range for human respiration. The main difference that you can see here is the implementation of a T in the sampling setup. The T allows for 2 different streams to come out of the reactor on the left, and so that flows into the bioaerosol sampler in the one stream, which stays constant at 2.5 liters per minute, and the other stream goes to a variable flow rate pump. And that flow rate pump was set to between 2.5 and 50 liters per minute. The results of these experiments showed that the inactivation of T1 as a challenge agent was inversely related to the combined flow rate. So at higher flow rates, there was a lower level of inactivation. However, at all flow rates between 5 and 52.5 liters per minute, the reactor was at least as effective as an N95 mask. That's indicated here with the green line, which represents 95% inactivation. So to conclude, the MFSD, when it was combined with the positioning device, allowed for measurements of fluence rate at precise locations. And then whenever measurements were taken with and without the reflective media, they demonstrated that the reflective media had a large impact on the photon recycling, which also had a large impact on the fluence rate of the reactor. When the 3 UVC reactors were tested, they were all found to have effective inactivation of T1 bacteriophage as a challenge agent at a lower flow rate. And then whenever the pod reactor was tested at variable flow rates, including higher flow rates, it demonstrated inactivation at least as effective as an N95 mask at those higher flow rates. I'd like to take a moment to thank all the contributing authors to this project and the presentation, especially Dr. Ernest R. Blatchley III, my PI, and Shing Li, who has provided much support, help, and guidance in the lab. I'd also like to thank our project sponsors and partners, AFWorks, the Air Force Research Laboratory, Purdue University, North Carolina State University, University of Colorado Boulder, and of course XCMR. Thank you very much. So I'll go ahead and leave that question actually to the later presentations for the design of the reactors. It had a reflectance of, we estimated to be 98%, but I'll leave that to the later presentations when the discussions are done about the device. Yeah, thank you.
Probably a little bit of jet lag, so I'm not paying attention. Close I should be. What microorganism, when you mentioned log reduction, were you using?
So the challenge agent that was used was T1 coliphage, or T1 bacteriophage. So that was done because it was both relatively safe to use in a lab setting, as well as because of its relatively conservative inactivation constant. So the question was, when comparing to an N95 mask, what's the consideration of fit for the N95 mask? So what I'm using here is the nominal value for an N95 mask, which is 95%. So that's proper fit when used in a proper way. It nominally provides 95% separation of particles 0.3 microns and larger. So that comparison is when an N95 mask is used properly, essentially. Yeah, that's a good question. So the question was about the distribution of the aerosol generator. I don't have an image here, but I believe the distribution centered at about 1 micron for the nebulizer. It was a 1-port Collison nebulizer was what was used. So the distribution of that is readily available online if you'd like to look at it.
A similar question on the flow rate with respect to if the rate was 5 to 50. Did you see any differences at the higher end versus the lower end? Maybe elaborate on that a little
Yeah, so for sure. So the first experiments were completed at 2.5 liters per minute, which was a relatively low flow rate compared to what would be indicative of human respiration. That provided very high inactivation because of the low flow rate. But then whenever the flow rate was increased to up to 52.5 liters per minute, we still found effective inactivation from the low pressure mercury lamp. But as you can see, the inactivation was inversely related to the flow rate. And so whenever we did those experiments, the fit of the nebulizer to the funnels that went into the reactor was also a looser fit to allow for makeup air to flow from the rest of the, this was done in a biological hood. So air was pulled from the rest of the hood, so it was essentially makeup air in addition to the T1. So it was also at a lower concentration of T1 entering the reactor.
So would the 52 be like running?
Yeah, 52.5 is more indicative of kind of usual average or higher respiration rates. It ranges between 5 and 50, and it can go up to a peak of maybe up to 90 at any instantaneous time. So.